So last time we covered areas between curves. Today we are going to cover inverse functions and how to differentiate them, which will be useful later on when we're talking about derivatives of various inverse functions. For now, we're skipping some sections in chapter 5. Well, the volume methods I'm not going to teach because they're kind of a waste of time, so I'm just skipping them. I will post some resources on them though, just in case some people might be interested in doing those. So in Calculus 2, it's very typical to teach things like finding volumes by cross-sectional area, the disks method or the washer method, and finding volumes of rotations by cylindrical shells and things like that. But you go to Calc 3, you learn much more efficient methods of finding volumes, and they don't never mention the Calc 2 methods, and you literally never use them ever again. Right? I've been a math major for years and had graduate degrees in mathematics. The methods that I learned in Calc 2, I've never seen them ever again. It's something that's only done in Calc 2, so I was like, yeah, forget it, it's not important. But for some of you might want to look at that stuff in case maybe you want to be a math tutor in the math help room and you know that people are going to come and ask you questions about it. Okay, I got it. I will post some resources to help you with that, but in this class I'm not going to actually do that. One thing that we are skipping that I will come back to is work, but we'll do that later in the semester. And for now we're skipping to chapter 6. So we're going to start with 6.1 where we're going to talk about inverse functions. Start by defining functions. I did this in my Calc 1 class, but hopefully we'll move a lot quicker here. What's a function? How do you describe a function?
It's when an input x gives an output y.
Mm-hmm. Does that until yeah?
It's a mathematical formula that relates the input to the output.
Okay. Does any formula work? Yeah?
For every x, there's a single y value.
Okay, that's the important thing. So yes, it is a rule or a formula that connects two groups of sets, but it connects them in such a way that each input has only one output. There are formulas that are not functions, like x squared plus y squared equals 4 is not a function. That's a circle, it doesn't pass the vertical line test, blah, blah, blah. Okay, so a function is a rule that assigns two elements of one set called the domain set assigns to each element exactly one element in another set called the codomain. The set of elements in the codomain that are assigned is called the range. Conceptually, this will be important for us to understand, especially when we're talking about inverse functions. We first have to know about functions, because inverse functions really reverse. They're kind of reversing functions, okay? And there are many ways you can represent these functions. You can talk about mapping diagrams. You can literally draw pictures of two groups of sets, and you can show a function is doing something like f of x. It's going to take x to another value we call y, and you can represent it by formulas. You can represent them by graphs. You can represent them by all sorts of things. Okay, but it's a very special kind of relationship of making a connection between two groups. Okay, so that's what functions are. What we're going to talk about today is inverse functions. That is, the guys that go the other way. there are some functions that have what are called inverses. And an inverse function is a guy that starts over here and takes this as the domain. And that's useless. I figured I had all these colors, I might as well use them. See, green is better. And it goes backwards, and we call this function the inverse of f, and the notation is f with a little minus 1. Okay. So those are the guys we're going to be talking about. Not all functions have inverses. You only one-to-one and onto functions have inverses, so we'll probably have to talk about that as well. A function is said to be one-to-one if the following is true. F of x equals f of y implies that x equals y. There are many formulations of that. That's one way. Another way. If x is not equal to y, then your outputs will not be the same. This is more in words. It never assigns the same value twice. These are very important kinds of functions. These are called one-to-one functions. Okay? So a function can only assign one value, but there's nothing to say that you can't assign everyone the same value as long as everyone's getting one. So something that looks like a function can take everyone here, and it can connect them to one guy here. And this guy could connect to one guy, and that guy could connect to one guy. This is an example of a function, but it's not a one-to-one function. In a one-to-one function, if this guy's connected to that guy, no one else can connect to that guy. They have to connect to different people. Okay? That's what a one-to-one function means. Okay? Maybe I should give you some examples. Don't know how in depth we will need here. Example. Y equals 2x plus 1 is a one-to-one. That's shorthand for one-to-one function. And you can show this by if f of x equals f of y, this basically means that 2x plus 1 equals 2y plus 1, then I can subtract 1 from both sides, and I can divide both sides by 2. So if this is true, then that must be true. So that's how you know something is a one-to-one function. Example, y equals x squared is not one-to-one. Since if f of x equals f of y, this means that your x squared is equal to y squared. But then when you take the square root of both sides, you get plus or minus y, and that's a problem. Right? It's possible to have the same outputs coming from different inputs, in particular when one is the negative of the other. Right? So you can imagine, for example, that f of 1 is the same as f of minus 1, but clearly 1 is not the same as minus 1. Right? You can also see this from the graph. So this is y equals x squared. Notice that at the y value 1, there are 2 x values that will map to that. Okay? So this is, you can also define a one-to-one function based on its graph, based on whether it follows the horizontal line test. Any horizontal line should only touch the graph one time, and you know the function is one-to-one. Now, went through that kind of quickly. I would assume you guys have seen one-to-one functions before. Okay. But why is it important that a function is 1 to 1 for an inverse. Right? So an inverse function is a function that goes backwards, meaning it takes this set as the domain and that set as the codomain. Okay? And why would something like this be a problem in that situation? Yeah?
Because it has more than one y value.
Because here would be an input, according to the inverse, that has 3 different outputs, right? So if you have a situation like this, you can have a function in this direction, but you will not have a function in that direction. If we take this as the domain, it's no longer a function, right? The only way you can make sure it's a function is if this property holds, where I can know that even if I think of this as the domain, there's only one connection going back that way. Okay? So that's why being 1 to 1 is very important. So there are going to be functions that do not have inverses. So in other words, that's what this is kind of telling you. If a function is not 1 to 1, it cannot have an inverse. It's also important that your function is what we call onto, which means every element in here is assigned. But we'll mostly be thinking about functions reversing from their range. So there's such a thing as having a range. Right, this is the set that would be called the range here of the function. Okay, so there could be elements in this set that aren't connected. We say they're not in the range. Okay, which means that's another reason why this cannot be a function going in the opposite direction. But we're not going to really see that right now. You'll really talk about that in higher classes. But for now, that's basically the idea. A function, in order to be invertible, as we say, or for an inverse function to exist, it has to be 1 to 1. And if we restrict it to the range, that's all we need. So let's get to that definition. Suppose f from A to B. This is notation, by the way. Not typically used in calculus, but you'll see it in higher classes, where this set is the domain, and this set is the codomain. So you could see something, for example, f goes from the real numbers to the real numbers, or f goes from the real numbers to the positive real numbers, or something like that. You can write functions down. Not typical, but it's easier for me to write down the definition. Not typical at this level, but later on, it's going to be very important for you to know where your functions are going, because there's going to be all sorts of sets. Okay. Suppose this function that goes from this domain to that codomain is a 1-to-1 function with range B, meaning everyone in the set assigned. Then there exists a function which we call f inverse that goes from B to A, such that if f of x equals y, it would mean that f inverse of y would be x. It's a function that undoes your function. It goes backwards. Okay? This is our definition for an inverse function. So there is a function. If you can take x and it outputs a value y, and that's done by your function f. If this function is 1-to-1 and the range is the entire codomain, there's another function that will take that output and give you back the original input. This function we denote by f to the minus 1. It is important for you to realize that f inverse of x is notation. It does not mean 1 over f. Alright, it's not the same. Okay? So this is notation for the inverse function. F inverse of x equals the inverse function of f. it might happen to be this, but it doesn't have to be that. Any questions so far? Mostly I'm just rushing through definitions. Yes?
Can you just explain quickly the notation at the bottom line on that side of the board?
This?
Yeah.
That's basically saying something like, if I have a function that when I plug in 2, I get 3,
Uh-huh.
and I know that it has an inverse, this means if I plug in 3 into the inverse, the output would be 2.
Okay.
In other words, the inputs become the outputs becomes the inputs. The domains and range switch, and it's like you're totally reversing the bizarro world in terms of functions. Okay, so that's what this is meant to say. So if your function is one-to-one and onto the codomain, there exists a function that essentially does the reverse. It will go from, it will use this as a domain and connect to that, such that all the guys that were connected in the original function are also connected in the reverse function, in specifically that way. And this is going to be one of the basic results that you prove in something like an advanced calculus class. Like, how do you know that this function has to exist? At this point, just trust me, it will exist under those conditions. I think I got through all the definitions now. Okay, let's talk about some consequences. These will help you in solving your problems. So here are some consequences, right? So F inverse undoes F. Okay. So you can think of F inverse as the undo function in Microsoft Office, right? It will just go back a step and undo what you just did, right? So you can think of it as just reversing the function. Another thing you should realize is that the domain of F will be the same as the range of F inverse. And the range of F is essentially the domain of F inverse. So ranges are in general very difficult to find. Domains are a lot easier. However, if you kind of know what the inverse function is, you can figure out the range of the original function by finding the domain of the inverse function. So that's something that might come in handy. Yeah, and this one is super important. You should mark that by a star. F inverse of f of x is, anyone guess what that is? Yeah?
1 over f prime of, oh no, x, sorry, it's just x.
It's just x.
Yeah, sorry.
You're all the way in derivatives already, we're not there yet, okay? If you take the function and you make a composite function with the inverse function, it pretty much undoes everything. So if you start with x and f does something, f inverse is going to just bring you back to the x, okay? This is true for all x in the domain of f. As well as, if you take f of f inverse of x, this is just x. And this is true for all x in the range of f. So if you compose a function with its inverse, it just gives you the original input. Okay? And that's going to be important. We're actually going to use that to prove something in a bit. First, let's talk about finding inverses. This is important, it's one of the finding inverses. Am I moving too fast for you guys, or are you following? I don't want to lose you because there's no point if I'm just up here talking to myself. Okay. If you need me to slow down, let me know. Because this business about functions, I know you've been beat to death with functions ever since like pre-algebra class. This is a function, this is a function, every class, this is a function, this is a function. Okay, so I'm just kind of getting through the non-new stuff. We're still in review mode, so I'm still going to be moving fast. When we get to actually doing calculus of this, I'll slow down a little bit. But if I'm moving faster, you let me know. Okay, so finding inverses. Two situations that can be helpful. One is graphically. Okay, so let's say you're given the graph of a function. How do you find the graph of its inverse, assuming it has one? Anyone tell me? Does remember? Yeah?
It's a reflection of the line y equals x.
Right. Given the graph of f of x, you can obtain the graph of f inverse by reflecting in the line y equals x. Okay. This isn't proof, but this is one of the way I justify to my Calc 1 students that logarithms and exponential functions are inverses. So if you have a function that looks like this, and this happens to be a one-to-one function, then if you have this line y equals x, this is y equals x, then if you take this and mirror it over there, that would be your inverse function. So this is your f of x, this is going to be your f inverse of x. Right? And it doesn't matter what the function is doing over here, if you reflect it in this line, that will give you the inverse function. Well, the graph of the inverse function. So you can sort of know what the picture is going to look like. And we'll do this when we talk about inverse trig functions. And you'll see me reflecting the sine function to figure out what is the sine inverse function, the cosine inverse function, and all that stuff. So that's going to be important if you're going to want to know how to graph something. And now I don't remember why I was confining myself to this board. I have this one too. Let's move over here. Another way is algebraically. So once, given y equals f of x, how do you find it algebraically? Do you guys remember from algebra class? So if I gave you a function, how do you find the inverse function?
You switch the x and y.
Switch x and y. That's what do you do? You solve for what? You will end up with y equals f inverse x. So again, it's this idea of switching the guys that represent the domain and the range, right? Because you're literally reversing everything. So you just flip everything, x switches to y. It's kind of also the idea why you reflect in y equals x, because now the y's are turning into the x's and the x's are turning into the y's. But that's how you would solve for an inverse function algebraically. By the way, there is a big caveat here, if possible. Because it's not actually always possible to solve for the other variable, but if I ever ask you to do this, it will be possible. Okay, so if you have a function and you want to find its inverse function, you switch the x and the y, you solve for the y. And then that result will be the inverse function in a formula. Let's actually do a couple examples of that. Example. Find the inverse function of the following. Or just a those things. Okay, how about the first one? What's the inverse function? Y equals x to the fifth minus 7 for inverse. Switch x and y, solve for y. So this gives x is equal to y to the fifth minus 7. This means this means your y would be the fifth root of x plus 7. This means f inverse of x would be the fifth root of x plus 7. So the function that will reverse this function is that function. So this took the fifth power and subtracted 7. What you're going to do is you're going to add the 7 back and then take the fifth root to get back the original. So that is your inverse function. What's the inverse function of the second one? What's the inverse of that? 1 over x.
I got 1 over x.
Switch x and y, you'll get x is equal to 1 over y, and then you solve for y, you clearly get y equals 1 over x. So it turns out that f inverse in this case is exactly the same as the original function. It's 1 over x. And shouldn't be strange to you because if you remember that 1 over x looks like this, if you flip x equals y, you'll get exactly the same picture. You can flip it over here. C. Y is equal to 1 plus x over 1 minus x. What's the inverse function? How do we solve that for y? Yeah?
Multiply the 1 minus y over, and then factor that out.
And then do what?
And then you can factor that out.
Factor what out?
Distribute
Or,
x.
sorry, distribute,
Distribute.
yes, thank you.
X minus xy equals 1 plus y.
And then get all the y's together on one side.
So this x minus 1 is equal to xy plus y. Factor out the y here. And then you can divide. So your y would be x minus 1 over x plus 1. And that's actually the negative reciprocal of that. What about D? How do you find the inverse function?
Same idea as A.
Okay, so if we switch x and y, switch x and y, we'll have x is equal to y to the fourth minus 4. And so what would you say here?
Add 4 to both sides and take the fourth root. And you have it.
Is that okay?
No.
What's the problem?
Well, that would technically be the inverse of it, but it's not 1 to 1. It's one.
Plus or minus.
Right,
Yeah.
because this would give you a plus or a minus, which means it's a toss-up. Could you actually fix that? So technically, this has no inverse. It was a trick question. As written, it has no inverse. Could someone tell me some ideas on how we could fix the situation? Let's say we want to find some sort of inverse in some sort of context. Yep?
You could restrict it to only x greater than 0.
You can
X greater
restrict it.
than-
Okay, so this function looks like, well, like that, like a parabola shifted down 4. Right? Where this here would be the negative fourth, negative fourth root, or positive fourth root. Okay. And so the thing is, if you look at that picture now, you'll notice that it does not pass the horizontal line test. There are a bunch of horizontal lines I can draw here that will touch this curve in 2 places. And so one way we can fix this is to what we call restrict the domain. Okay? So I can literally just cut off a piece of this function and only keep a part that I care about that will pass the horizontal line test. So one way to fix this, well, you can't really fix it, but sometimes you don't care about everything. Sometimes you might not care about the negative part of a function for some reason. It's called restrict the domain. For example, you can consider y equals x to the fourth minus 4 for x greater than or equal to 0. You can only care about half that function, and that will have an inverse. In fact, that would have the plus sign here. Or if I care about the half where the x is negative, I will take the negative sign. Okay? But sometimes you have to restrict an inverse. You might choose what part of a function you care about and ignore the other part just to get something else to work. In fact, when we find inverse trig functions, we are going to have to do this because you might notice that sine and cosine do not pass the horizontal line test. Okay? So their inverse functions aren't globally defined. We're going to have to actually cut off a piece of them, and your inverse function will only work in a small area, and that will show you why trig had all these weird rules that you might have remembered back in pre-calc. About, oh, the sine inverse, it only works in here, it only outputs in this range, and blah, blah, blah. It's because of this. Okay. Another issue. Sometimes we can't find the inverse algebraically, but probably make more comments about that, but maybe you guys can remind me to come back to it. Or the finance outcomes. Example. Okay, so in A, f of x equals x cubed plus 2x minus 1. I want you to find f inverse at 2. B, f of x equals x cubed over 4 plus x minus 1. F inverse at 3. Okay, how do you find the inverse of the function at the point 2? Yeah?
First switch the x and y to solve for y, and then you find the inverse and plug into it.
So if I say x equals this, how would you solve for y? Can use the cubic formula, but it's super messy. I probably
Yeah, I
wouldn't
just
do that.
realized
But I didn't ask for the inverse function, I asked for the value at 2. How do you use that to your advantage? Yeah.
Couldn't you set the x cubed plus 2x minus 1 equal to 2, and then find the x value that satisfies that?
Yeah, so we want, yeah, exactly, f of inverse of 2. Okay, set that equal to something. Say set f inverse of 2 equals x. This means, by one of the rules I gave you earlier, that 2 must be equal to f of x. Right? Which means that x cubed plus 2x minus 1 should be equal to 2. And I end up, to find this specific value, I end up having to solve that specific equation. Can you give me any ideas? Yeah.
You can pull the 1 over to the other side and yank out an x. And then factor out an x from the left side.
Uh-huh.
It'll be pretty obvious which number it says.
I don't think that would be obvious. There's something even more obvious. If you had to guess, what would you guess? Yeah?
Factor out the x.
Okay. Yeah?
It's just 1.
X equals 1. So when you do something like that, what he just did was he just saw, hey, 1 plus 2 is equal to 3. You say you've done it by inspection. Oh yeah, I knew this answer by inspection. This will not work in all contexts. Don't think you can go on one of my tests and write all the answers down. Oh, by inspection. That's not how it works. If you have a particular equation that's difficult to solve, which if you're given a problem like this, it will be, the idea is they're going to want to actually like see the answer. There are ways that you can solve something like this and know that x equals 1 would be an answer. Something like the rational roots theorem, which you might remember from algebra. Do you guys remember rational roots theorem? that would be something like if you're given x cubed plus 2x, you bring everything to one side, minus 3 equals 0. It turns out that if there are nice numbers that will solve this equation, rational numbers, meaning whole numbers or fractions, then they will have a certain form. They will be the factors of the constant term divided by the factors of the leading coefficient. So the possible nice values for this would be something like plus or minus 3, plus or minus 1 would be the only possible nice values, and you would just guess those, right? So you can guess according to the rational roots. Sometimes. Sometimes it'll be hard to see, but for polynomials, that would be kind of where you're guessing. So if you're intimidated by guessing, it's something you're going to have to learn how to do, because in real life, math is not as straightforward and nice as it is in calculus class. A lot of times you just have to guess something and try to work something out. So it's something you want to start getting used to. Not being able to actually physically work out an answer, but to actually start with nothing, essentially, and get something out of it. We'll probably finish those off later. Just want to sort of end with a formula in case any of you want to go ahead on your homework. We'll finish these examples later. But let's talk about differentiating inverse functions. So let's say we're given f of x and it's invertible. Then if I take f inverse and I want to differentiate it, that x, it turns out that will actually be the form of 1 over f prime of f inverse of x. Alright, provided this exists, meaning the denominator can't be 0, all that stuff. And you might be wondering why. Well, the answer is the following. Let's say I have f of f inverse of x. What is that equal to? It's equal to x. Now if you differentiate both sides with respect to x, on this side, how do you differentiate as something like this? Chain rule. Differentiate the outside function, leave the inside alone, and multiply by the derivative of the inside function. This side, derivative of that is 1. Okay? This is the guy we're after. As long as this isn't 0, we can divide by it. And hence we have that formula. Meaning that if we have a function, we know it's invertible, we can actually differentiate the inverse function using this formula. And we will use this formula to derive the derivative of all sorts of inverse functions. So if we know, for example, the derivative of sine of x, we can figure out what the derivative of sine inverse of x is using this method, for example. It's just all applying the chain rule. So usually when we're using this, again, we want to do at a specific point, which basically means to plug in this value here, you're going to make a guess, and that will end up helping you to solve the problem. But we will pick up with that next time, because I believe time is up. We're done at 12:20, right? So next time we'll do the rest of the examples that I skipped, and we'll actually talk about this. Yes.
Are you taking a homework?
Yes. Also leave your. Uh, 6.1 is not due yet because I haven't finished it, but the homework for 5.1